Okay, so the aim of this talk this morning is to really give you some background for the work that I intend to do here during a visit in Cambridge. So the aim is to look forward to soliciting your interest and your interactions during the next couple of weeks. That's my objective. The basic question I'm interested in is predicting the reproducible features of turbulent flows. Now, this doesn't exactly sit in on a program focusing on extreme events, but I think a theory of the statistics of extreme events ought also to predict the reproducible mean behavior of such flows. So it may be a useful point to start with. And the question is, what is the relevant and irrelevant physics that we need to put into that theory? Do we really need the full detail of the Navier-Stokes equation, or can we get away with something simpler? There are many different approaches, but two I would like to contrast with each other is the bottom-up one, where you try as far as you can to represent the Navier-Stokes equation in some detail and predict the flows from numerical simulations. Contrary to that, there's more of a top-down approach, which takes a variational approach. Variational principles, as you know, permeate all of physics, and especially equilibrium thermodynamics, so it's natural to ask whether such variational principles also apply in non-equilibrium statistical mechanics. And there the idea would be to replace the full detail of the Navier-Stokes with a variational principle which is constrained by only certain integral properties of the Navier-Stokes equation, a reduced set of dynamical constraints. And both of these approaches raise fundamental issues. On the bottom there, just the sheer complexity, but also you end up having to truncate the Navier-Stokes equations anyway with a finite resolution model. Then at the top, of course, is the fundamental question of what it is we should be maximizing or minimizing in this approach. And crucially, what is the constraints that we need to put in, the relevant physics that we think we ought to put into that approach. So I'll be focusing, well, just to end there, the point I want to make in this slide is that both approaches involve truncating the dynamics in some sense, by necessity at the bottom, but willfully in the top. We want to try and see how much we can get away without. The question then is, what level we truncate and how we deal with the things that we're not resolving. And in this talk, I'm going to focus on a particular variational principle that's emerged in three different independent ways throughout the last 50 years or so, focusing on maximizing kinetic energy dissipation of turbulent flows. So the three roads are represented here. And really they all lead to various versions of a maximum kinetic energy dissipation principle. And our aim in the next couple of weeks is to try and tie these independent rows together to see the theoretical links between them so that we can gain a better understanding of the theoretical foundation for that variational principle and guide us in using it in applications for example, climate systems. So it's really trying to tie together these three threads. So let's start with the first one, and it goes back, like many of these threads, to the 1950s and the work of Wilhelm Malthus on the upper bound theory of turbulence, and leads through my more recent dynamic stability analysis to this variational principle. So I just want to outline the major steps in that thread leading to maximum kinetic energy dissipation for turbulent channel flows. And these are two seminal papers in the 1950s, which essentially Malthus conjectured that in thermal turbulence or shear turbulence in channel flow, the velocity field self-organizes, or the mean velocity field self-organizes so as to maximize the transport of the relevant quantity across the channel, heat or momentum. And you can do some remarkable things with that very simple idea, which is illustrated here. If one has thermal convection and one actually idealizes the temperature profile to be constant in the middle and then just have a linear variation within the boundary layer, then one can, and then Malthus also proposed that this maximization of the transport was related to marginal stability of the boundary layer. That marginal stability criterion leads to a relationship. So you're saying that the relevant Rayleigh number for the boundary layer is critical, and from the simple diffusion equation for transport within the layer, you can then relate the rate of transport across the entire surface system to the Rayleigh number for the whole system, and that has a power of a third, which is captured, broadly speaking, by the data. Very difficult to get that result in any other way. So marginal stability seems to be a crucial thing. If you do the same trick for shear turbulence, you get assuming that the boundary layer is again marginally stable, we get a linear relationship between the Reynolds number and the maximal momentum transport. So there's a promising approach there. Of course, no foundational basis. So later on, in order to actually calculate the velocity profile explicitly, rather than assuming that idealized form, Malthus and a whole series of other individuals developed what's known as the upper bound theory of fluid turbulence, in which they attempted to reproduce the mean features of velocity profiles by maximizing various dissipation-like functionals of the flow, and to a lesser or greater success. Kerswell, for example, in 2002 tried various functionals where d is the total kinetic energy dissipation of the velocity field, dv and dm are the kinetic energy dissipation of the fluctuating and the mean components. And he looked at a whole family of these functionals, and he concluded rather pessimistically that there didn't seem to be some unique one that worked in all cases, and that we were left with this rather unsatisfactory situation where we just have to do it by trial and error. Nevertheless, some hope arrived shortly afterwards when Malthus, the originator of this whole approach, revisited this classic problem in his beautiful paper called Borders of Disorder, in which he provided a dynamic stability argument for a particular choice of dissipation functional that should be maximized. And that argument has three key steps, which I'll just outline here. The first is that rather than looking at the stability of a given solution, he looked at what would be a sufficient condition for instability of some steady state solution of the flow, which has some Reynolds decomposition here. So he's looking at a perturbation, and of course the perturbation will grow and be unstable if its kinetic energy increases over time. That's a classic thing, but the second key element, very clever, was that Malthus only restricted his attention to a subclass of perturbations in which were proportional to the fluctuating component of another second steady state solution. So it's in a sense he's looking at competition between two steady state solutions. Who can destabilize who? The third key element of Malthus's analysis was, instead of using the complete Navier-Stokes equation to do this, he only used two integral constraints derived from the Navier-Stokes equation, just the overall energy balance, like kinetic energy in is dissipation, and secondly, horizontal mean momentum balance at each level within the channel. And from that, he showed analytically that the original flow is unstable to this special subclass if the competing solution has a greater kinetic energy dissipation of the mean flow, not the total, but the mean flow. In other words, a necessary condition for the stability of our original flow is that it should be maximal in that quantity. It's such a beautiful, sort of simple result. One would wonders whether there's a more physically intuitive interpretation for the end result of this rather sort of mathematical procedure. It turns out there is one, and Jason Bertram, my student, will be talking about that later this afternoon. But that's the result that Malthus obtained. And it belongs to that family that Carswell looked at in this way. So that's the talk Jason's going to give on Malthus's dynamic stability analysis. Does it work? Well, he applied it to the classic problem by maximizing the kinetic energy dissipation of the mean flow, so that's the mean flow rate, subject though to two key extra conditions. There's that marginal stability of the boundary layer appearing as before, and also he eliminated any solutions which had inflection points, which is a sort of Rayleigh instability criterion for inviscid flow. And this is the result he got for the velocity profile that maximizes that quantity. And this is on the logarithmic scale, that this is the channel across the channel, and this is the normalized velocity profile. We get the viscous sublayer here, we get the logarithmic inertial sublayer here, moving up to a defect layer in the middle of the channel. And not only those shapes are correct, but the numbers are correct to within 10% of the data over 2 orders of magnitude of Reynolds number, a remarkable result given such a simple model. So that was encouraging. So that's our first road. So now I want to move up to the climate. We've been talking about channel flows. A totally different story, an independent story, starting, as you may know, in the 1950s and early 60s, when Ed Lorenz proposed that the atmospheric circulation self-organizes in such a way as to maximize the total generation rate of available potential energy in the atmosphere, which is equal through the cascade to the total dissipation of kinetic energy in the system, the so-called Lorentz cycle. So this is going to be a brief story, because it's not really my field, and I'm conscious of the time. So a couple of slides on that story. This is the Lorentz cycle, and so G here, max G, is the generation of potential energy from external heating, like solar heating, plus also recycling of frictional heating from dissipation. And this increases the potential energy. We get a conversion to kinetic energy and a dissipation rate. So he's basically proposing that this cycle goes as fast as possible under the constraints of the system. He and various subsequent workers proposed heuristic arguments for why the system might self-organize in that way, but nothing approaching the rigor of Malthus's dynamic stability argument, for example, for channel flow. Nevertheless, does it work? Here is a simulation of a GCM. It's a low-resolution version of a Hadley GCM called FAMOUS, Atmospheric Ocean GCM, in which they calculated or estimated the total dissipation of kinetic energy in the system through what they call the energy correction. It's the amount of energy they have to put back into the system in order to preserve energy conservation in the thermodynamic equations. And so that's total dissipation. And this graph shows the sensitivity analysis of that total kinetic energy dissipation in the climate system to two particular parameters, 2 out of the 100 that you mentioned earlier, which involve various aspects of the system, but essentially you can think of these things changing the velocity, the flow patterns within the climate in the steady state. And they found this peak, which in these two parameter space, which lies within the bounds of reasonable values for these two parameters. So it seems that that peak makes contact with realistic climate. And that's an observation. Again, it's just a GCM. There's no theoretical foundation for that principle. Nevertheless, it has echoes of what Malthus found. But if you remember, Malthus was maximizing only the kinetic energy dissipation of the mean flow in channel flow. This is the total. Again, Jason will be talking a little bit about this later on. So that's the second road. And the third thread, another totally independent bit of the history of climatology, began with some seminal papers by Garth Paltridge in the 70s, in which he claimed he could predict certain gross features of the heat transport in the Earth's climate from a maximization principle of maximum entropy production. And again, another variational approach. And this has led more recently to a theoretical approach to this, to try and provide a theoretical foundation for Partridge's model, which leads us again to maximum kinetic energy dissipation for certain turbulent flows. So I want to go through that story, the last in our 3 roads. So this is what Partridge did. He had a very simple one-dimensional model of the climate system, which is zonally average. So this is the different latitudinal zones from the North Pole to the South Pole. And in each of these 10 boxes, he represented the surface temperature, the cloud fraction, and the inputs and outputs of radiation. And then he also had meridional interzonal heat flows between these boxes. And basically by trial and error, he had no idea what he was doing. He just said, let's try and construct various things which, when I maximize them, look like the real world. And this is what he came up with. He said, if I maximize this quantity, which is the net radiation output divided by the temperature, and add them up over each box, and I maximize that with respect to these interzonal heat fluxes, then I only do that subject to global energy balance. And then, as I show you, I get some interesting results. But before I show them, the key point here is that there is absolutely no dynamics in this model. It's the only constraint is total energy balance. It's an energy balance model. So of course it can't work, okay? Anyway, he's assuming that we don't need any dynamics at all, at least as far as predicting the heat flows of the system. And this is what he found, that the predicted and observed latitudinal profiles in temperature and cloud cover look rather realistic. More recently, a similar energy balance model, no dynamics, but involving longitudinal as well as latitudinal heat transport, was evaluated by Herbert and Payat. And they showed that the meridional heat transport, that's these horizontal fluxes I showed in this diagram here, reproduce reasonably well what you actually simulate in a full GCM. Again, remarkable. Look, no dynamics. What's going on? Good point. So in Partridge's original model, there were several parameters he could tune, but he didn't tune them, but there were several assumptions in there which you could say forced the result or conditioned the result. That was the reason why this later study eliminated many of the ad hoc features of Partridge's original model, particularly in the radiation balance scheme. But this result has been reproduced by a whole suite of different models that go beyond Partridge's. Now this idea of maximum entropy production has actually been applied in various forms right across physics and biology, and to things like the evolutionary optimization of important biological molecules like ATP synthase, the selection of different morphological growth patterns of crystals, the light reactions of photosynthesis, plant and ecosystem adaptations. We talked about turbulence before in this kinetic energy dissipation story, earthquake dynamics. But like Malthus's, like the upper bound theory, some intriguing successes, as we've just seen, but no theoretical foundation whatsoever. So this is just some kind of fluke, or what's going on here. So the work that I've been doing over the last few years is really an attempt to put all of these variational principles on a more fundamental theoretical foundation. And the approach that we have taken is the approach of maximizing the Shannon entropy. And that is an approach that's appropriate because it's, as we heard in talks earlier, Shannon entropy has a good definition, whether you're in equilibrium or non-equilibrium. And the approach of non-equilibrium statistical mechanics based on maximum entropy in this way was pioneered by Ed James in the 50s and 60s. So again, another story that began in the 50s. So where does this lead us? If we, before just going on, I should just say that there is a statistical rationale. Okay, so maximum entropy says you should maximize this. Actually, this is the relative entropy with respect to the distribution. So it predicts a distribution, a statistical distribution, not just the mean behavior, but the fluctuations also. So this will be relevant for extreme events, subject to certain constraints. And the rationale, or at least one rationale, is that this distribution so constructed coincides with the most likely frequency distribution of outcomes that you would observe in a long series of observations in the large n limit under given constraints. That's to say that you will observe that only if the constraints you assumed here are the ones that actually apply in the real experiment, and that's the key of this game, identifying those key constraints. But that's a very simple statistical interpretation of what we're doing when we use maximum entropy. We're getting the most likely frequency distribution of results. So when we apply this to flow problems, of course it's all in the constraints, as I just said. So we're going to be interested, as I said, in looking at the statistics of some flow field. It could be velocity field and turbulence, or heat transport in the Earth's climate. And we're going to use maxent subject to various constraints on that distribution. And generically, the key ones we're interested in are various, for stationary states, are various steady state constraints on the fluxes, things like global energy balance, for example, or momentum balance in the case of Malthus's experiment, for example. But a restricted number of them, not the full dynamics. That's the key thing. We're only hoping that big M is a small number. Secondly, we put in what's called a trial flow field, okay? And that's very much in the spirit of variational principles, where one supposes a trial solution and then one varies the trial solution to maximize or minimize something. So that's exactly what we're doing here. The third and crucial dynamical assumption that we put in is that there's some minimal dissipative state which is unstable. That's to say that we're forcing the system far enough for equilibrium that, for example, we're beyond the critical Reynolds number for laminar flow. And we encode that in a strict inequality, which is encoded with respect to this measure of irreversibility. It's formally the Kullback-Liebler divergence of the probability of F and the time reversal of F. So it makes connections with the fluctuation theorem that we heard yesterday. If you're in equilibrium, P of F is equal to P of minus F, this thing is 0. So it's a measure of how far we are from equilibrium. It's also strictly non-negative by the Gibbs inequality, so we get a sort of second law inequality just from the mathematics of the definition. And what we're saying is that the minimal irreversibility state, which we suppose is related to the things like laminar flow, is dynamically unstable. And the natural question then is to see how big that quantity can get. We're assuming there's some upper bound because you have a finite forcing. The system can't be infinitely far from equilibrium. So there's some upper bound as well. And the question is, where does the system sit? If it's pushed away from this, how far does it get up to the top? Well, maxent predicts it gets all the way. Maxent predicts that if we put these constraints into maxent, then a system in which this minimal irreversibility state is dynamically unstable will actually, the most probable state it will live in is this maximal irreversibility state, a state of maximal time reverse symmetry breaking. We don't yet have, at this stage, any idea of what the physical significance of this thing, other than it's a measure of how far we are from equilibrium. But the theory, the maxent calculation, significantly gives us that too. It says not only that we get to the top but we know what the physical or thermodynamic interpretation of that is, and here it is. The irreversibility as a function depends on the actual constraints that we imposed. So it depends on, and there are two particular cases depending on the symmetry of the dynamical constraints, and we'll come to that. These are the dynamical constraints we put in at that point there, and we'll see examples of that. But basically the punchline is that Maxent tells us not only that irreversibility should be maximized, but it also tells us explicitly what the thermodynamic interpretation of that irreversibility is. It depends on the constraints you put in. There's no universal quantity that's maximized in all problems. It depends on the constraints. So two examples of how that works out in practice. Let's go back to Paltridge. What Paltridge did was essentially was interested in looking at the meridional heat fluxes, and so we're interested in the probability distribution of those meridional heat fluxes, subject only to one single steady state constraint, which is global energy balance. Then according to the theory of Maxent, that calculation, that irreversibility is actually precisely the one that Paltridge picked out by trial and error. The theory tells us that given that that is the only constraint we're putting into Maxent, then this is the object that should be maximized according to the theory. So we have a theoretical foundation for Paltridge's MEP result, and it's telling us that according to the results, that global energy balance is the only relevant key constraint that you need to put in if you want to reproduce the overall heat transport patterns of the planet. Yep, nearly done. Let's now look at Malchus, the first road that we explored, and this is now, we're looking at F as the velocity field in turbulence, and we have the Navier-Stokes and dimensionless form up there for quasi-flow, and the two key integral constraints that Malchus put into his calculation, if you remember, was global power balance, so kinetic energy in is dissipation, and this is this equation here, so it's just the velocity field dot product into that equation. And the second one is horizontally averaged mean momentum balance at each level of the channel. So not the full Navier-Stokes, just those two integral constraints. So when we put that into our theory of Maxent, it tells us that what we should be maximizing, that irreversibility measure that we put into the theory, turns out to be precisely the dissipation rate of kinetic energy in the mean flow, precisely what Malchus derived from his dynamical stability argument. So it's an intriguing connection that we get the same result from two apparently different theoretical routes. And I just want to underline the fact that it seems from the theory that what you maximize depends on what you assume to be the relevant physics. In Paltridge, it was just global energy balance, and the relevant thing was this, what we call this material entropy production. But if you're interested in predicting actual velocity fields, not just heat transport, then obviously you need to put in some more dynamics, and that's the momentum constraint that Malchus put in. And in that case, the maximal function is kinetic energy dissipation. And this is what's found, this is the graph I showed before, there's a maximum in the kinetic energy dissipation, but not in the Paltridge functional, because we're looking at different constraints, different problems. If you're interested in the applications of maximum entropy production and the underlying theory that I've outlined, you might find this book of interest. What we want to do finally, to finish, given these three roads, what we want to do here in Cambridge is to link them up in order to gain insights into how general this kinetic energy dissipation variational principle is. In particular, why is it that it's the mean dissipation of the mean flow in the Malchus context, for turbulent channel flow, but it may be kinetic energy dissipation of the total in the case of the climate system. We want to tie up these theoretical threads and try and get insights into why these things work. So there are three key routes that we're going to try to do that. We would be very interested in getting your inputs to that. The first is to try and understand the theoretical link between a dynamical stability argument here and a statistical argument here. Does it mean that is there a maximal irreversibility? Is that synonymous with maximum dynamic stability? We'd like to understand that link more precisely. Secondly, can we extend the maximum entropy production analysis for climate from heat transport to the actual velocity fields themselves, and apply and perhaps derive a maximum kinetic energy dissipation like principle from this route? And lastly, Malthus's dynamical stability argument was very much constrained by that particular geometry of that particular flow. Can it be generalized in some way to give us insights into maximum dissipation of kinetic energy in the climate context, again to theoretically underpin this whole game? So I'd be interested in your thoughts and comments on that over the next 2 weeks. Thank you.
Okay, thank you very much for not following my deplorable example. Sticking to time, we have time for a couple of questions.
Yeah, but there was a theorem by Prigogine on maximum entropy production that certainly does not hold in this situation, but may have prompted those three authors to.
Yes, and of course the variational principles associated with the dissipation and maximum entropy production go back to Onsager, and even before that to Raleigh and so on. So
I must say that actually when I was still a master's student in mechanical engineering, I was quite fascinated both by Prigogine's little book in Methuen, and by James and so on. And the first topic for my master's that I registered had to do with that, but that's not what happened. I eventually got heat transfer to a common vortex tree by other means. So, okay, Eddie.
So it seems that in your talk there is a confusion between maximum entropy and maximum entropy production. And I mean, several times you speak, it's not clear what you were talking about.
yes, so there's an intense confusion in the literature between the different uses of the term entropy and so on, and part of what we've been trying to do in this theoretical foundation is to tear these apart. There's a clear distinction between the Shannon entropy, in the way that we use it, and this entropy production, which actually comes out from the irreversibility constraint. They're two quite different things, and there is a great need to untangle the semantic confusion in the literature.
What you call theoretical basis. I mean, in statistical mechanics, we are used to talk about theoretical basis when we try to deduce this from first principle, for instance, from dynamics. So it doesn't seem to be the case. It doesn't seem to be what you do here.
No, it's quite a different approach, and it's interesting to try and marry them. But the James approach is a very top-down approach. It starts with a guess for the relevant constraints, and then predicts the Maxent distribution, and then you see whether that works in the real world. That complements, if you like, a bottom-up dynamical systems approach, but it is distinct from that. Yeah.
Yep. I just have a comment there. There's some other work by a student of Swinney, and they also maximize and subject to certain constraints and understand pretty well velocity distributions in turbulent Couillard-Taylor flow. So I think there are a couple of different groups having similar ideas, which should really be united in this approach. And the crucial question is always, what do you put in as a suitable condition of constraint? That is very much subject to personal taste sometimes.
Yep.
And what would be good theory if one could really give theory that gives these constraints from first principles.
Totally agree.
Okay, last one.
Yes, I think it's not completely excluded, however, the other principle of minimum rate of entropy production, because the thesis of Prigogine basically was the minimum rate of entropy production, and the Partridge came later with this proof that at least in atmosphere we have a maximum rate of entropy production. But I think it's a matter of regimes, because Prigogine was talking about a system which is close to equilibrium.
Yep.
And while if you drive strongly a system, then he will try to do them to settle it somehow, so you will produce as much disorder as possible. Now, my question is the following, however, for the first part of your talk, which was very interesting, I think. When a system is close to ideal state, it does not dissipate, of course, by definition. However, there is a small dissipation, and that dissipation takes place precisely where the streamlines are broken and reconnected. So they are associated with topological changes of the fluid. The energy remains quasi stable for a long time, just losing very small amount of energy. It's called actually the places where this happens is fractal. Okay, and in this case, if the nature would choose to maximize the dissipation, to what change in topology correspond this? We are far from ideality indeed, but however, what is the reason for doing that?
I can't.
Eddy turbulence, reconnection, crazy turbulence, reconnecting the reformation of eddies and other ways. I mean, it must exist a mathematical spirit of the combinatorial sense of the entropy there.
I think this is a long question, so maybe if we do want a coffee break, we can discuss it.
We can discuss.
Okay.
Thank
Thank you again
Good
very
question,
much.
though. Thank you.